Hey guys, Jake here coming at you with another math lesson today at 5 o'clock Pacific time every Monday night. A little bit late today, sorry about that, but give or take a couple minutes. But today we're going to be going over a topic which obviously if you click this video, you probably already know it's going to be implicit differentiation. I came out recently with a video where I really talked about like the actual steps that you would go through to solve an optimization problem. If you want to check that out, I do think it might be a pretty helpful video for you if you want to learn more about optimization problems. But I want to follow kind of a similar format to that in this video, just about a different topic, which is implicit differentiation. So basically what we're going to do is we're going to go over the exact steps that you can go through basically to solve any implicit differentiation problem that you might come across in a differential calculus class. Basically, I'm just going to be giving you kind of a blueprint that you can use whenever you're trying to solve these types of problems on your own. And then once I kind of go through the actual steps that you would go through, we're going to go ahead and go through a couple examples so I can show you exactly how to apply these steps. So first of all, we're going to start with implicit differentiation. And we're going to start just by talking about the steps. We will get into examples shortly, but let's start there. So whenever you're doing any implicit differentiation problem, typically what the problem asks you to do is basically find dy dx is probably the most common thing that it would ask you to find. It may say something like dx dt, for example. That's another common situation that might come up. But essentially what you're trying to do is find the derivative of some function with respect to some variable. If it's dy dx, you're saying find the derivative of y with respect to x. And the type of problem that they would give you would just be some equation which relates x and y. However, it's typically not just going to be y equals some function of x. Because if you're given something like this, your y is already solved for, and you can essentially just use different derivative methods that you may know, like power rule, chain rule, product rule, quotient rule, certain derivatives that you've probably memorized. If you're given something like this, you can typically just apply those. But the type of situation where you have to apply implicit differentiation is where you have x's and y's all kind of mixed together, and you can't solve for y and get it all by itself. And that's why the differentiation is considered implicit, because we don't have an explicit formula for our function of y. So we have to use this kind of different method. So in terms of the actual steps that you want to go through, basically the first thing you want to do is look at your problem that you're given. First of all, figure out what is your function and what is your variable. So determine your variable and your function. Now, when I say that, what does that mean? Well, let's say, like I said, we are given some equation which relates x and y to each other, but all the x's and y's are all mixed together. Let's say the problem told us to find dy dx. This little thing right here in parentheses, find dy dx, this actually tells us the answer to step one. It tells us what our variable and what our function are. If you have d something over d something, whatever this letter is on the bottom right here, that's going to be your variable. And whatever this letter is on the top here, in this case it's y, is going to be your function. Okay, so dy over dx, our function is y, our variable is x. If we're told to find dx dt, that right there tells us our t is our variable and x is our function. So that answers step one right there. Sometimes they may not say find dy dx or find dx dt, and you have to use context clues. In that case, you want to figure out basically what is your independent variable, what is the variable that you would plug in, what would be your input variable, and that's going to be your variable. And then whatever is your dependent variable or your output variable, whatever the output of your function is, that is your function. So in this case, the x would be the independent input variable, and y would be the dependent output variable. In this case, dx dt, if you were in a situation where it didn't say find dx dt, but it gave you some sort of relationship between x and t, where t was an independent input variable and x was a dependent output variable, that would tell you that t is your variable, x is your function. And what you're looking for is dx dt. So that is how you want to start. Okay, so once you have figured out what your function and what your variable is, what letter represents each of those things, at that point you need to take the derivative. So essentially take the derivative of both sides of your equation with respect to whatever your variable is. So take the derivative with respect to your variable. So we're taking it with respect to whatever you determined was your variable up here in step 1. So if we're finding dy dx, we're taking the derivative with respect to x of both sides of our equation. Okay. Once you do that, you should end up with, so doing this step 2, that's basically just going to be, you may have to use different things like power rule, product rule, quotient rule. When you're doing that, what you want to be very careful of is any part of your equation that only contains x's or only contains your variable, you're just going to differentiate as normal. However, any parts of your equation that include y or whatever your function letter is, you need to be sure to treat your function as a function of your variable. You need to treat y as a function of x. And when I say that, that's going to be a little bit easier to explain with an example, which, like I said, we'll be getting into shortly. But typically, whenever you have your y or your function letter and you're taking the derivative of that chunk, you typically are going to have to use chain rule, because you have to keep in mind that y is an unknown function of x. So that is going to end up kind of using the chain rule in most situations. And like I said, I'll get into that a little bit more when we do the examples. Okay, so then once you've taken the derivative with respect to whatever your variable is, what you want to do is you want to move all of your terms that contain dy dx over to one side of your equation, and move all of your terms that do not include dy dx over to the other side. So basically separate your dy dx terms and your non-dy dx terms. Get them each separated on each side of the equation. Typically, what that's going to look like is just adding or subtracting terms that have dy dx over to the left side of your equation, for example, and then adding or subtracting any terms that don't have dy dx over to the right side of your equation. Once you have done that, you're going to look at the side of your equation that has your dy dx terms, and you're going to factor out a dy dx, because every term on that side of the equation at that point should contain dy dx. So if you factor the dy dx out, what that basically does is it simplifies your left side of your equation, or whichever side of your equation it is. It simplifies it into a situation where you just have dy dx times a bunch of stuff in parentheses. And the reason why that's important is because what that does is it creates a situation where you only have a single dy dx term at that point. Right? So after step 3, after step 2, where we take the derivative with respect to our variable, after you do that, there's typically going to be multiple dy dx's, because there was probably multiple y's in your equation before. Once you do that, it's kind of hard to solve for dy dx until we get to this 4th step, because what that does is it simplifies multiple dy dx's, kind of condenses them down into a single dy dx. And why that's great is because once we have done that, we can pretty easily move everything that is on the same side of the equation as the dy dx over to the other side of the equation, typically by just dividing that whole side of the equation by whatever's in the parentheses. So move other terms away from dy dx side of the equation, which essentially kind of the idea there is we're just trying to isolate or solve for dy dx. So once you've done that, you should just have at that point dy dx equals a bunch of stuff with just x's and y's usually on the other side of the equation. So that's an important thing to keep in mind. Once you do this, you're probably going to have x's and y's in your answer. And that's okay. And that's why we had to do implicit differentiation, because if we were able to just get dy dx equals something with x's in it, we probably wouldn't have had to use implicit differentiation, because we could have just taken the derivative explicitly, because we would have had an explicit equation for y. So that's basically the steps. So now I want to show you some examples of how to actually use those steps. If you are getting some value out of this video so far, do me a favor and go ahead and hit that like button so we can get this video out to more people and help grow the Jake's Math Lessons community and learn calculus together. And as always with these live streams, if you do have any questions along the way, throw them in the live chat. I'm happy to help address questions the best I can. Even if they're not on topic, just throw those in the live chat. I'll see if I can answer them live, but if not, I should be able to circle back and hopefully answer your question in another video. But let's go ahead and get into an example. So like I said, basically what these problems typically say is they'll just tell you to find dy dx, and they'll just give you some equation which contains x's and y's. So let's just say maybe we have some equation, x times y equals maybe y times, actually, let's say this, x times sine of y. Okay, so this is our equation which has x's and y's all mixed together, and basically what we need to do is find dy dx using implicit differentiation. So first thing you want to do is figure out what is your variable, what is your function. Well, looking at this problem, it's telling us that we need to find dy dx, whatever is up at the top of our equation, in this case it's y, that's going to be your function. And whatever is down here on the bottom is going to be your variable. So basically what that tells us is y is a function of x. The reason why that's important is because now what we need to do is take the derivative of both sides of our equation with respect to whatever our variable is. Since our variable is x, because that was on the bottom here, as a result of that, we need to take the derivative of both sides of our equation with respect to x. So taking the derivative of this function with respect to x, basically that just means of both sides. So first of all, we need to find the derivative of x times y. Well, if you have x times y, that's a product of two different functions, basically, where one of your functions is x and one of your functions is y. So we need to use the product rule. Product rule says we're going to first decide what is f and what is g. Doesn't really matter which one you pick for which. So let's just say f is x, g is y. Then you need to find f prime, which is just the derivative of f. The derivative of x with respect to x is just 1, right? Because this term right here only has your variable in it, so pretty much taking the derivative of it is going to behave the way you would expect it to. The derivative of x is 1. Now, for finding the derivative of y, that's where you need to keep in mind that y is an unknown function of x. So to take the derivative of some function of x, if we don't know what the actual function is, we just know the function is called y, the best we can really do is to just say the derivative of y is just the derivative of y with respect to x. Well, how do you say that? That's exactly what dy dx is. So dy dx is going to be the derivative of y, and that's going to be our g prime. Okay, so product rule says we're going to cross multiply these and then add the results together. So x times dy dx plus 1 times y, which is just y. Okay, so that's the derivative of the left side of the equation. Now, on the right side of the equation here, again, we're going to have to use product rule because we have x times sine of y. So we have the product of these two functions here. So again, we need to determine what is f, what is g. Let's just say f is x, g is sine of y. And then we need to find f prime and g prime. Derivative of x is 1. Now, for the derivative of sine of y, that's where it gets a little bit more tricky. So I said earlier when we were talking about kind of the steps that you would go through, whenever you're taking the derivative of something with your function, typically you're going to have to use chain rule. And the reason for that is you want to think of y as a function of x. So don't think of this as sine of y. Think of it as sine of some unknown function of x, right? If you were taking the derivative of this, you would have to use chain rule because you have this inner function here and then this outer function that it's being plugged into. Sine of f of x is a composite function, so we have to do the chain rule. So chain rule says we're going to do the derivative of the outside function, leave the inside function alone. So we're going to take the derivative of sine, which is cosine, leave the inside function alone. So we're going to take cosine of y, and then we're going to multiply that by the derivative of the inside function, the derivative of y. Well, the derivative of y, just like we found over here, is just dy dx. So we're going to multiply that by dy dx. Okay? Product rule says we're going to multiply these across and then add them together. X times cosine y times dy dx. Plus 1 times sine of y is just sine of y. Okay, so we've done our differentiation step. We've taken the derivative of both sides of our equation. Now what we need to do is add and subtract all of our dx or dy dx terms to one side of the equation and then all of our non-dy dx terms to the other side of the equation. So let's kind of just sort out, first of all, where are our dy dx terms? Where are the non-dy dx terms? So this term right here has a dy dx. This term right here has a dy dx. And then the other terms do not. So this term right here does not have a dy dx, and it is this one. So basically, we can move our dy dx terms over to the left, move our non-dy dx terms over to the right. So to do that, if we have a plus y right here, we just need to minus y from both sides. If we have x times cosine y times dy dx, we would just need to minus that over to the other side. So minus that from both sides. And what that's going to do is the y is going to cancel there. The negative xy dy dx is going to cancel with the x cosine y dy dx. So we're just going to be left with, at that point, x times dy dx minus x cosine y dy dx equals a positive sine of y minus y. Okay? So then, once we've done that, the next step is to factor out dy dx from your dy dx side of the equation. So both of the terms over on the left side of our equation here have a dy dx. So what we can do is we can factor those out of the left side of our equation. So we're going to be left with x. If we take dy dx out of this first term, the x is going to be left. If we take the dy dx out of this term, we're going to be left with minus x times cosine y. And then obviously we didn't do anything to change the right side of our equation in this step, so we'll just keep that the same. And then now that we only have a single dy dx term, and that's the thing we're trying to solve for, to get that by itself, all we have to do is divide by everything within the brackets here. And of course, whatever we do to one side of the equation, we need to do to the other side as well. So dy dx is going to equal sine of y minus y all over x minus x cosine of y. And that's going to be it for that example. So if that all makes sense so far, do me a favor and drop a comment. Say, got it so far, so I know you're following along. And we'll go ahead and jump into one more example here. Let's say in this case, we are going to find dx dt, where we have x over t equals, let's not do that. Yeah, x plus cosine of t. Okay. Okay, so we're going to go ahead and find this by implicit differentiation. So we have this equation which relates x's and t's. First thing we want to do is figure out which of these letters we want to treat as our variable and which one we want to treat as a function. So since we have x on top, we're finding dx dt and dt on the bottom. That right there tells you x is your function and t is your variable. Okay, so we're going to treat t as the variable, x as the function. As a result, what we need to do is take the derivative of both sides of our equation with respect to our variable. So we're going to take the derivative of both sides of our equation with respect to t. So we're going to take d dt of this whole equation, both sides of it. So taking the derivative of the left side of our equation with respect to t, remember we need to treat t as a variable, x as a function. Well, we have a fraction here, so we're going to use quotient rule. Quotient rule says that what we need to do is we need to first determine our top and our bottom. So f is going to be your top function. G is going to be our bottom function. So f is x, g is t. Then you want to find f prime and g prime. The derivative of f, or the derivative of x with respect to t. So keep in mind here, t is our variable. We're taking the derivative of x, which is a function of t, with respect to t. So since x is a function, an unknown function of t, the derivative of x is not just going to be 1. That would be the case if we were taking the derivative with respect to x. But since we're taking the derivative with respect to t, we need to treat x as a function. If x is an unknown function of t and we take the derivative with respect to t, the derivative of x is just going to be the derivative of x with respect to t. Dx dt literally just means the derivative of x with respect to t. We don't know x, so we can't know x's derivative either, but we can say the derivative is dx dt. Okay? Then we need to take the derivative of g, which is t. The derivative of t with respect to t is just 1. Okay? Now, quotient rule says we're going to do low d high. So low times the derivative of high, the derivative of the top. So t times dx dt. Low d high minus high d low. So minus f times g prime. So x times 1 is just x. And then that's going to be all over the bottom squared. Our original bottom function is t. T squared is going to be our denominator. Okay, so that is the left side of our equation. Now, for the right side of our equation, we need to take the derivative of x. Well, the derivative of x is, again, we need to take the derivative of x with respect to t. T is our variable, x is a function. Just like we said here, the derivative of x with respect to t is dx dt. So x is going to become dx dt, and then plus the derivative of cosine of t. The derivative of cosine of t would actually be minus sine of t. So instead of plus, I'm going to write minus sine of t. Because t is our variable, this term right here only contains our variable that we're taking the derivative with respect to. So that's going to behave as expected. The derivative of cosine is minus sine of your variable t. Okay, so this is the end of the differentiation step. If that makes sense so far, do me a favor, say, got it so far, just drop a comment below, and we'll keep on going along. If you do have any questions, as always with these live streams, throw them in the live chat. I'll do my best to answer whatever questions you have along the way. Okay, so now that we've taken the derivative of both sides of our equation, what we need to do is move all of our dy dx terms to one side of the equation, move all of our non-dy dx terms to the other side. However, in this case, it's a little bit of an added step, kind of like a pre-step to that, because having this fraction here kind of makes that difficult. So what we actually want to do first is basically get rid of the fraction by multiplying that over to the other side of the equation so that we have everything all on one line, like no fractions basically, other than the dx dt, of course. So that's going to cancel with that. We're going to be left with t times dx dt minus x equals, and then what I'm going to do is go ahead and distribute this in. So we do want to do that as well. So basically, kind of a part of this moving all the dy dx terms or dx dt terms to one side of the equation and the non-dx dt terms to the other side, you kind of want to think ahead to that. What you kind of want to do first is typically expand your whole equation out. Get rid of all your parentheses, distribute those out, get rid of your fractions, multiply the denominator over to the other side. Just get everything expanded out as much as possible, because that is going to put us in a situation where we can add or subtract the dx dt terms over to one side of the equation and the non-dx dt terms to the other side. So t squared times dx dt is going to be t squared dx dt, and then minus t squared times sine of t. Okay, so now this is fully expanded out. There's no more real simplifying we can do here to, or maybe that's not simplifying. Simplifying would be like factoring out and stuff. We want to do the opposite. We want to get it fully expanded out so that now what we can do is we can just simply subtract all of our dx dt terms over to one side of the equation and vice versa. So actually, this is kind of an interesting problem. Let's see here. Did I make a mistake somewhere? No, I don't think I made a mistake. I think I picked a very weird example. Sorry about that. Let's see here. Because what's about to happen is if we subtract our dx dt terms to one side of the equation, they're all going to cancel each other out, which we don't typically expect with these implicit differentiation problems. All right, well, I guess that is just the cost of doing things live sometimes. Well, because what we're about to do, typically what we would want to do at this point is minus all of our dt terms to one side. So we would minus t dx dt in order to move it over to the left side of the equation. But you see what that's going to do here is it's going to cancel that out fully from both sides. And it's going to leave us with minus x equals minus t squared times sine of t, which we would not really expect. So this is a very odd problem if I didn't make any mistakes, which I'm wondering if I may have done. So let me, sorry about this, guys. Where would that be? If anybody spots a mistake, feel free to throw it in the live chat as I look back through here. So let's see, low d high minus high d low all over low squared dx dt, the derivative of cosine would be negative sine, okay. And then let's see here, times the t squared over, distribute that through. Oh, yes, I see my mistake. All right, let me back up. Sorry about that. Reverse that, reverse, reverse, reverse. It is right here. When I distributed this into this term right here, I wrote t times dx dt. That is not correct. It should be a t squared. All right. Sorry about that. That is more like what I was expecting to see there. So let's carry on from there. So we get that t squared times dx dt, and then t squared times negative sine of t leaves us with this. Okay. So now what we need to do, like I was saying before, let's circle back to that. We need to subtract or add all of our dx dt terms to one side of the equation and our non-dx dt terms to the other side. So first thing I like to do is just kind of circle, where are my dx dt terms? Where are my non-dx dt terms? So you can see in blue here, we have dx dt here and here. And then in red, I put this minus x and this minus t squared times sine of t do not have a dx dt. So basically we want to move our, dx dt term over to the left and our non-dx dt term over to the right. So to do that, basically we are just going to minus this t squared dx dt from both sides, minus t squared dx dt from both sides. And then we're going to add x over, plus x, plus x. We're going to do that to both sides. That's going to cancel that there, and then it's going to cancel that there. So we're going to be left with, on the left side, t times dx dt minus t squared times dx dt equals negative t squared times sine of t plus x. Okay. So then once we have gotten all of our dx dt terms to one side of the equation, so you can see every term over here on the left side now contains a dx dt, and every term on the right does not contain a dx dt. So once we've kind of separated those out, what we can do, since every term on the left side of our equation has a dx dt in common, we can factor that out of the left side of our equation. So we'll pull dx dt out of the left side, and what's that going to leave us with? If we take a dx dt from this term, we're going to just be left with a t. If we take dx dt out from this term, we're going to be left with minus t squared. Okay. We did not do anything to the right side of our equation. All we did was factor out something from the left. So this is going to remain unchanged. And then now we've gotten this equation to a point where we only have a single dx dt term, which is great, because from there, to get dx dt all by itself, which, remember, the problem said find dx dt, that's what we were originally told to do. What we're trying to do is solve for that dx dt, which now we only have one of. So to get it all by itself, all we have to do is divide all this stuff right here that dx dt is being multiplied by. So divide by t minus t squared, divide by t minus t squared. That's going to cancel the t minus t squared on the left, leaving us with dx dt equals everything over here. Whoa. Whoops. And that's it. If anybody has any questions about that, feel free to throw them in the live chat. Happy to help address whatever questions we have. Even if it's off topic, throw any questions you have. I'm happy to help address whatever questions you might have about calculus in general. But otherwise, that's the end of that problem. That's all I had prepared for you guys. So if you did get some value out of this video, if you found something here helpful, do me a favor and hit that like button. It's a huge help to my channel so I can keep making more videos like this. And be sure to hit that subscribe button and bell icon while you're down there too. We'll keep crushing it all term long in calculus, keep boosting up your grades, getting you closer to that A you're hoping for. And not seeing any questions, so we'll go ahead and wrap things up there. Thank you for all joining. Hopefully I see you next week, next Monday night, 5 o'clock Pacific time for my live stream next week. And we'll go from there. Have a good rest of your week.